Consider the following 2018 Poland Mathematical Olympiad problem number 5. And here's a view of this problem. An acute triangle ABC, A, B, and C, in which AB, side AB measures less than side AC is given. Points E and F are the feet of the altitudes drawn from vertices B and C of our triangle ABC. The line tangent in point A to the circumcircle of triangle ABC crosses BC at P, so AP is tangent to the circumcircle of triangle ABC, and it crosses BC, segment BC extended at point P. The line parallel to BC, well, that would be this line AQ, crosses EF. Recall that F and E are the feet of the altitudes. So crosses EF extended at the point Q. We would like to prove that PQ, this red line, P stretching from the point and connecting the points P and Q, is perpendicular to the median AM. So therefore M is the midpoint of segment BC. Well, what I would like to do here is to provide two solutions to this problem. One of my viewers mentioned that the Polish Math Olympiad is approaching next month, and I was just searching. I opened the 2018 questions, and this question seemed interesting. So here is a very simple solution to this problem that I got from AOPS. I forgot the name of the user. Let me quickly check. AOPS user GG Piku, and the technique is very standard, though might seem controversial at the same time. So it is the following. So it's based on the idea that of the existence of two cyclic quadrilaterals. The first quadrilateral is BFEC. BFEC is cyclic, and I think this is quite clear because angle BFC and BEC are both 90-degree angles. They subtend diameter BC. In a sense, the center of this circle, BFC, is BEFC, is the midpoint of segment BC, namely point M. Awesome. So I think that this one's clear. Well, the second one is this dotted circle that I have added here into the picture, and it is the fact that AFHE is cyclic. AFHE is cyclic. And this is also clear because if you consider segment AH as the diameter of that circle, I think it's quite clear. So the midpoint of segment AH would be the center, because angle AFH is 90 degrees, as is the angle AEH. So therefore, these 4 points, AFHE, are indeed cyclic points. Now, to the solution of this problem. The claim is that PQ is the radical axis of two circles, and indeed, if I can show that, well, okay, so let's first investigate which two. So I claim that PQ is a radical axis of the following circles, namely circle A. And when I say A, I mean the point A. You can consider it as a circle with zero radius, and circle BFEC. BFEC. Now let's quickly check why that's the case, because if that's indeed the case, and indeed if PQ is a radical axis of those two circles, because those two circles, their centers are in points A and M respectively, like I mentioned here. This one is obvious. This one is also clear because BC is the diameter and M is the midpoint. So that would clearly show that PQ, the radical axis, is obviously perpendicular to the line segment AM, which connects the centers of those two circles. But AM, incidentally, is also the median from A of triangle ABC, and as such, that would prove the problem. But so why would that be the case? Well, the result is based on the following fact. Well, the fact is the following: QA, the line parallel to BC at point A, is a tangent to the circumcircle of this circle AFHE. And if you recall an earlier video that I posted, it's called the three tangents lemma. From that lemma, that result should be clear. And you guys can just simply check that lemma. Just simply search on YouTube as the three tangents lemma. So therefore, because it's just a simple angle chasing, to be honest, nothing fancy. So because AQ is parallel to BC and it is tangent to AFHE, I can calculate the power of point Q with respect to that circle. So the power of point Q with respect to circle AFHE is, well, QA squared. But QA squared, or you can alternatively write it as QE times QF. Now, what's interesting is that QE times QF happens to be also the power of point Q, an expression for the power of point Q with respect to the circumcircle of quadrilateral BFEC. And that's clear, right? So we established earlier that BFEC is cyclic. As a result, that thing is also, which is, so QE times QF is the power of Q again, but this time with respect to circle BFEC, which is a circle, and AFHE was also a circle. We can interpret QA square as well as the power, QA square lastly can be interpreted as the power of point Q with respect to that circle, that point circle, if you will. And so let's write it down. So therefore, we have that QA square represent, and let's write it, QA square is also the power of point Q again with respect to circle A, and boom. So from there we have that, well, QA square, which happens to be equal to QE times QF, is the power of circle A, but it's also the power of circle BFEC. As such, Q is on the radical axis of those two circles. By a similar token, we can also show that P is also in such a position. It's on the radical axis of these two circles. Well, first of all, the power of point P with respect to point circle A is just PA squared. But PA square, if you focus on the circumcircle of triangle ABC, because PA is tangent to that circumcircle, PA square is also equal to PB times PC. So let's write that down. PA square is equal to PB times PC. But PB times PC is just the power of point P with respect to the circle BFEC again, BFEC. And like we said, PA squared can be interpreted as the power of point P with respect to circle A. And boom, again, we have the same result. So because P has equal powers with respect to these two circles, it must lie on the radical axis of these two circles. Now, Q is on the radical axis of those two circles, A and BFEC. P is also on the radical axis of those two circles, A and BFEC. As such, because those two are on the radical axis, PQ must be perpendicular to the line segment connecting the centers of those two circles, A and BFEC. The center of circle A is A, the center of circle BFEC is M, and boom. So we have the desired result. So therefore PQ, the radical axis, is perpendicular to the line segment connecting the centers of those two circles. Now this was a solution for this problem. One can go also one step further and analyze this picture more carefully. There's actually very deep construction behind this picture, a lot of projective geometry going on. And I want to illustrate this, but before I can do so, I need to show three short results. And if you want to stop here, you can stop watching here. But if you want to go further and look at a second solution, which is really really beautiful and connects quite a lot of results, is the following. So first I need to establish a couple of results from projective geometry first. So we can start with Laffers Theorem, or I think the English speakers call it Laffers Theorem. It states the following: if A is on the polar of B, or we can say A is on the polar of B if and only if and only if B is on the polar of A, polar lines. And let me quickly draw a picture and prove this important result, and then we can go further. So we have the circle omega, our reference circle, O its center, and we have this point. I will just analyze one of the cases where point A is outside the circle, and you can find similar results or establish similar results for if the point is inside the circle. So what's the definition of a polar? The polar of a point A is just the perpendicular line drawn at the inverse of that point. So if you call this point as the inverse of it, so it's this line over here. So we usually represent it with the symbol A perp, and so where here A and A prime are inverses of each other with respect to omega. An alternative construction for this is quite nice. All you do is you just draw tangents from this point outside the circle, and it so happens that these tangents lie on that polar line as well. And so these are some very well-known results from geometry about inversion. And I can quickly establish the following result, if you will, showing the relationship between the point A and A prime as it relates to the radius of our circle. So this is a 90-degree angle, and so we have this 90-degree angle as well. I'm just going to show that indeed A and A prime are inverses of each other if we have this construction where we draw two tangents from A to the circle omega, and you can just focus on triangles. Well, first I think it's clear that these two angles are congruent angles for obvious reasons. Well, obviously because this is a 90-degree angle and so on. So yeah, it's clear. I hope we have two right triangles inside each other. Awesome. So and obviously triangle ACO, as a result, ACO is similar to triangle CA prime O, CA prime O, and this would imply, by chasing the lengths, that say for instance AO to CO, yeah, that would do. AO to CO is congruent to I can use I need AO to CO, CO to A prime O. and boom. So this would give us the desired result. CO square, which happens to be just the radius square, is equal to AO times A prime O, which is the definition of the inverse of a point. Well, let's go back to Laffers theorem. Now we pick any random point on it, on the polar of A, say this point B, and it's clearly on the polar of A. So let me just get rid of this part. Awesome. So what I will do is I will connect this point B to the center of our circle, and I will further draw a perpendicular from point A, and let me do it with a different color, from point A to that line, line segment BO, and I will mark this point here as B. Let's just mark it as X for now. Yeah, as X, and I will show that X is the inverse of point B with respect to that circumcircle. And well, I think it's obvious, because if you focus on triangles AXO and triangle AXO BA prime O, BA prime O, triangle BA prime O. I hope it's clear that these two triangles are indeed similar by angle-angle similarity. Well, obviously both triangles have 90-degree angles, and besides they share this angle as well. And well, if these two triangles are similar, again you can write some length relationships associated to these triangles. For instance, let me see. We can check the ratio of AO to BO. AO to BO is congruent to, well, XO to A prime O. XO to A prime O. But then again, this would imply, because AO times A prime O, we established earlier, is R square. So this implies that R square is equal to BO times XO. So therefore, this implies indeed that X itself is nothing but the inverse of the point B. And we have the inverse of the point B. And we have a line which is perpendicular, namely line AX, which is perpendicular to it. So therefore, but this is the definition of the polar line, like I mentioned early on, right? Remember that the polar line is a line drawn perpendicular to the from our point to the center of the circle, and this is that's the definition. So therefore, what we have shown is that AX is the polar of the point B, and indeed it goes through the point A as desired. So starting with a point B on the polar of A, we have found that A has to be on the polar of B. So therefore, A is also on the polar of B by the given result. And like I said earlier, that would imply also that we have these tangencies as well. So obviously this is not clear, but pretend this is the tangency point between the circle and the and this segment. Awesome. So this was the first theorem I wanted to show. A second theorem, which is relevant for the purposes of our problem, is the following one, and then I'll directly go to the problem. I don't want to take more of your time. And this is the following result, which is quite useful again. If you have a triangle ABC, and you can find this result on AOPS contest page as well, related to this 2018 Polish problem. It turns out that let's go ahead and establish the following points first. So you draw the perpendicular from point A, and we can also draw the perpendiculars from point B and C to clearly mark the orthocenter H of triangle ABC. And we can label these points as E and F. It turns out that if you draw two circles, namely this circle AFHE, which we have also used in the first solution, and also this new circle, the circumcircle of BHC, which I can draw like this probably. Yeah, okay, so this is horrible, but okay, I guess you guys well, it makes sense of that. So the claim is the following. The claim is that the intersection, the second intersection point between these two circles, for the time being, let's label it as X. We claim that X lies on the median of segment BC. So which is in that case the point M. The point M, well, the picture is not that clear after all. But anyhow, I hope, yeah, so I'm not confusing anybody. So the claim is that, so this is another theorem, sometimes referred to, well, I don't know, so sometimes it's, I guess, referred to the HM theorem, somehow relating the orthocenter with the median, the midpoint of segment BC. And the claim is that, like we said, the intersection, let X be the intersection point of circles AFHE and BHC. Then the claim is that then X is on AM, which is the median. And the proof is along the following lines. So we construct a parallelogram. So basically BAC and then A prime. So which will probably look like this, I would say, kind of, I hope. Yeah, why not? Okay, so pretend this is the point, and let's call this point for now A prime. So this is a parallelogram suggesting that this angle is also A, and obviously, for instance, these two angles are alternate interior angles. As a result, this angle is C, for instance. So we can prove the result in two steps. Well, first, because it's a parallelogram, the diagonals bisect each other, and because M is the midpoint of segment BC, I think it's clear that AA prime, the diagonal goes through M, right? So therefore, we have A, M, A prime are collinear. So this is the beginning of the proof. Well, the first thing to notice is that the point A prime lies, we claim, on the circumcircle of BHC. So A prime lies on the circumcircle of BHC. And, well, why would that be? Well, it's clear that if you measure angle BHC, and let me do it over here, BHC, if you measure this angle, we need to show that it is, because this angle here is 80 degrees, so we need to show that this angle here is 180 minus 80 degrees. Well, first of all, if you focus on this angle is just 90 minus C, because on right triangle BEC, obviously if this angle is C, this one should be B 90 minus C. By the same token, if you focus on right triangle BFC, this angle here is 90 minus B. So as a result, so this angle BHC on triangle BHC would simply be B plus C, but B plus C is the same thing, because if you focus on triangle ABC, is the same thing as 180 minus A, and boom. So therefore, we have shown that A prime is indeed on that circle. So let me just pretend that circle. Yeah, so it should go through that point A prime. So that's the first step. Now, in the second step, we need to establish that X, this point X, is indeed on that diagonal. So, which goes through the point M. We don't know for the time being if X is on that line. So what we can, what we can do is we can focus on two angles. Firstly, AXH. I think it's clear that angle AXH is 90 degrees. Because AH is the diameter of that triangle, so indeed if you get, and X is on that circle obviously, so this angle is 90 degrees. So all we need is to establish that HX A prime is also 90 degrees. HX A prime is also 90 degrees. But why would that be? So basically showing that this is 90 degrees is the same thing as saying that HA prime is a diameter, or if you will, A prime is the antipode of H with respect to that circle BHC. So why would that be? So how can we establish that HA prime is the diameter? Well, we just did it. Look at this angle over here. This is 90 degrees because 90 minus C here. Why was that angle C? Because of alternate interior angles here. Remember, we have a parallelogram. AB, A prime, C by construction is a parallelogram, and boom. So HA prime is a diameter, and as a result, HXA prime is also 90 degrees. But you have two 90-degree angles. They add up to 180. As a result, X must be on that diagonal AA prime of parallelogram AB A prime C, and we're done. So with these two results in mind, I'll go ahead and go back to our problem at hand. I have a second picture of pretty much the same problem, and this time I did add quite a few additional circles and lines and things like that, and along the way I want to mention a few other quite interesting results. But back to our problem. Again, we have our triangle ABC. Again, this is 2018 Poland, a second solution, Polish Math Olympiad. AM is the median of triangle ABC, and P is the intersection of BC and the tangent at point A to the circumcircle of ABC. AQ is parallel to BC, and Q is such that it is on segment FE. Well, it is on ray FE, I should say. Okay, so let's combine some of our results. Well, first of all, like we said on our earlier result, AFHE, the circle is there, this dotted red circle, and BFEC, that circle, this dotted circle is there too. Well, I should say, sorry, FBHC. Those two circles, they intersect at X, and X is that special point that I just mentioned early on. You can call it, it doesn't have any special name. You can call it the HM point, if you will. That's at least how it is considered in the literature, in a sense, in the AOPS literature at least. So, well, we have already established that HXA is 90 degrees if you want to use it, which I won't in this solution. So the solution is again from AOPS contest page due to user fast like a rabbit. And the result is the following. So we have this point X, which is the HM point, and well, the claim is that M is on the polar of point Q. Well, why would that be? Well, we need to establish that QX is tangent to that circle AFHE. So in order to establish that, first let's establish, because I want to use Laffers Theorem. Remember from the three tangents lemma, we have proven already that ME and MF are tangent to, so let me write that down, ME and MF are both tangent to the circumcircle of AFHE, and this result is sometimes referred to as the three tangents lemma. It's on Evan Chen's book, it is lemma 1.44, I believe. And I have another video where I have proven this result, which is again a simple angle chasing again. But that means that EF, if that's true, so this implies that EF is the polar of M, right? So M polar is just the line EF, but wait, Q is on that line. So Q is on the polar of M, and by Laffers theorem, this implies that M is on the polar of Q by Laffers theorem, or Laffers theorem, depending on which country you're from. But where is that line? So where is the polar of Q? I claim that AX is the polar of Q. So in order to establish that, I need to show that QX is tangent to that circle AFHE. Can you see why? This this was probably a distracting question. Well, the result is already staring at us. We have already known, again by this three tangents lemma, that QA is tangent to that circle AFHE. And so already we know that A is on the polar of Q. But again, by Laffers theorem, we have already established that M is also on the polar of Q. As a result, AM is the polar, and as a result, the point X, which is on that polar line, if you will, on that median, and on that circle AFHE, has to be that tangency point. So we have just established that QX is also tangent, but then by the equal tangents, QA and QX are congruent. So therefore, triangle AQX is an isosceles triangle. Awesome. So AQX is isosceles. Now the second part, I need to also show that APX is also an isosceles triangle. So by simply showing that PA is equal to PX. For that result, I will do the following. I will first calculate the power of P with respect to the circumcircle, which is PA square, but it's also equal to PB times PC. So PA square is equal to PB times PC, and this by power of a point at P with respect to the circumcircle of ABC. Okay, it's terrible handwriting. But wait, PB times PC is simply equal to PX square. Why? Okay, hold on. Let me just see that. Yes. Okay, so this is simply equal to PX square. Okay, why? Because of that orange circle. I don't know if you can see that circle that goes through that point A and then traces through X as well. Well, it happens to be that that circle is the Apollonian or the Apollonius circle of triangle ABC. If you wonder what that circle is, again, you can just check on different websites like AOPS, but it is quite a very well-known circle, and the center of that circle happens to be where the tangent at point A to the circumcircle of ABC hits BC, but we have that point already, and it's the point P. So therefore, P is the center of that Apollonian circle, and well, that implies that PA must be equal to PX because both A and X are on that circle. So therefore, PA square must be equal to PX square. But wait, if PX square is equal to PB times PC, because B, H, X, and C, they were all on a circle, it must mean that PX is tangent, implying that PX is tangent to that circle BHXC. Whew. And yeah, but well, obviously we don't need it, so we already know that PA square is equal to PX square, so therefore that would imply that PA is equal to PX, and as a result, again, triangle APX is also an isosceles triangle. So we know that AQX is isosceles, APX is isosceles, two isosceles triangles, they have the same base AX, so therefore the line, if you draw perpendiculars from P to AX and from Q to AX, they should meet at the same point here, and that's it. So you have just shown that PQ is perpendicular to AX, and we are done with this result. Well, obviously I try to minimize the use of projective geometry with just the use of this Laffers theorem. There's quite a few harmonic quadrilaterals here, so you could have used perspectivity, which is a very important feature of projective geometry in establishing the results much faster than what I did. But yeah, so hope that helps. And looking forward to see you guys in our next lecture.